All right, guys, take two on this thing. I just recorded an 8-minute video and I forgot to turn my microphone on. So you'll see in front of me the old video, and I'm going to make the exact same thing all over again. I hate when that happens. Anyway, we all make mistakes. Today we're going to be talking about the Coriolis effect, and I want to start with a slide that's actually in your ocean notes. So we're going to start here. Move my face out of the way. There it is. Okay, so the Coriolis effect is something that is a little bit tricky, a little bit hard to understand, because there's a lot of like physics and stuff going on with this. It's all due to the rotation of the Earth. So the idea is that air, which is not directly attached to the Earth, is going to move in a different way than what you might expect. It actually curves or deflects across the surface of the Earth due to the fact that the Earth is spinning. So I brought my globe home with me. And if you take a look at the globe and the way the Earth rotates, so I'm going to spin this globe in the direction that the Earth's rotating. Okay, get that centered on the screen. So the Earth spins like this. And if you look at the North Pole, which you're all looking at on the screen right there, the North Pole in the northern hemisphere, it looks like the Earth is spinning counterclockwise. Okay, but if I turn it around and you take a look at it, now it looks like the Earth is spinning clockwise. So in the southern hemisphere, it's clockwise. In the northern hemisphere, it's counterclockwise. And that's totally going to influence the direction that the wind is moving. Now remember, the direction that the wind is moving is going to directly influence the direction that the ocean is moving. The ocean currents are moving. Okay? And so the Coriolis effect is the idea that because the Earth spins or rotates every day, all the time, the air is going to like deflect or curve, and therefore the ocean currents are going to deflect or curve. Now this video right here, which I'm going to play for you, is going to describe that whole idea. So I'm going to play that right now.
If you've ever watched the news during a hurricane or wintertime nor'easter, you've probably noticed that big storms spin over time as they travel. In the northern hemisphere, they spin counterclockwise. But if you were watching a storm in the southern hemisphere, you'd see it spinning clockwise. Why do storms spin in different directions depending on their location? And why do they spin in the first place? A storm's rotation is due to something called the Coriolis effect, which is a phenomenon that causes fluids like water and air to curve as they travel across or above Earth's surface. Here's the basic idea. Earth is constantly spinning around its axis from west to east. But because Earth is a sphere and wider in the middle, points on the equator are actually spinning faster around the axis than points near the poles. So imagine you were standing in Texas and had a magic paper airplane that could travel hundreds of miles. If you threw your airplane directly northward, you might think it would land straight north, maybe somewhere in Nebraska. But Texas is actually spinning around Earth's axis faster than Nebraska is, because it's closer to the equator. That means that the paper airplane is spinning faster as well, and when you throw it, that spinning momentum is conserved. So if you threw your paper airplane in a straight line toward the north, it would land somewhere to the right of Nebraska, maybe in Delaware. So from your point of view in Texas, the plane would have taken a curved path to the right. The opposite would happen in the southern hemisphere. An object traveling from the equator to the south would get deflected to the left. So what does this have to do with hurricane spinning? Well, at the center of every hurricane is an area of very low pressure. As a result, the high-pressure air surrounding the center, or eye, of a storm is constantly rushing toward the low-pressure void in the middle. But because of the Coriolis effect, the air rushing toward the center is deflected off course. In the northern hemisphere, the volumes of air on all sides of the eye keep getting tugged slightly to the right. The air keeps trying to make its way to the middle and keeps getting deflected, causing the entire system to spin in a counterclockwise direction. In the southern hemisphere, where the Coriolis effect pulls air to the left, the opposite happens. Storms spin around the eye in a clockwise manner.
Big takeaway from that video was the idea that in the northern hemisphere, the air is going to deflect to the right. Okay, so up here to deflecting to the right, and this is a big thing. I would write this down if I were you. Northern hemisphere deflects to the right, and in the southern hemisphere it deflects to the left, and I'm going to show you that in a second. But the idea is, as a result of that, and this is going to get into some meteorology stuff later on, as a result of deflecting to the right in the northern hemisphere, all those low pressure storms like hurricanes have a counterclockwise rotation. And in the southern hemisphere, they have a clockwise rotation because they deflect to the left. Now, a couple of guys they're pretty big YouTube guys, Veritasium and Smarter Every Day, they put together a joint YouTube video, and they show how this counterclockwise and clockwise rotation happens in Australia as well as in the United States. So I'm going to play that video for you right now.
Hey, it's me, Destin. Welcome back to Smarter Every Day. Here's the deal. I've created a video in the Northern Hemisphere, and Derek from Veritasium has created one in the South. You have to synchronize these two videos in order for this to make any sense, but it's totally worth it if you do. So click the first link in the video description, get the video ready, and then synchronize on my mark. You ready? 5, 4, 3, 2, 1, booyah.
Today, we're trying something that's never been done before. I've made this video, and Destin has made a video on Smarter Every Day, and we want you to play them both at the same time. So there's a link to his video down in the description. Find a way to load both of these videos and then synchronize them on my mark. In 5, 4, 3, 2, 1. In Sydney, Australia, we are at 34 degrees south latitude.
Which is the opposite side of the world from Huntsville, Alabama. So, which way did the toilets flush?
That is the question.
Here in Huntsville, Alabama, we're at 34 degrees north latitude.
And we're gonna find out if the water swirls the opposite way here to how it does in the southern hemisphere.
We're making the definitive video to settle this once and for all. It's never been done on the internet. You're gonna learn something.
The Simpsons did a whole episode based on toilets flushing the opposite direction in Australia. Plus, other shows have supposedly demonstrated this effect.
So I've seen documentaries that seem to indicate that which hemisphere you're in determines which way the water is going to swirl. But there's this other group of people, and they seem really confident that it doesn't matter where you're at, the water's going to swirl however it wants.
So is this a real effect or not?
The application of this principle to draining water in Earth's two hemispheres is just bunk.
But have you ever just looked for yourself and figured out which way your toilet swirls?
If you try it yourself, you'll find inconsistent results.
Here in Alabama, I've noticed that some turn counterclockwise and some go clockwise.
This sink sometimes drains one way and sometimes the other way.
You see, most toilets have little jets in it, so the swirl direction is determined by the design of the toilet and not which hemisphere you're in.
In any container of water, there's always going to be some rotation. The water is not perfectly still. And it is this, rather than the hemisphere, that determines which way the water will swirl down the drain.
So it's a myth. Crossing the equator does not mean the toilet's going to change directions. But what if we come into the garage and do a more controlled experiment?
But what if we could eliminate all motion from the water?
This is a 1.5 meter kiddie pool.
I have here a 5-foot wide kiddie pool.
Instead of filling the pool with no vorticity at all, I'm going against the way it's supposed to drain. So I'm trying to fill it with the flow going clockwise.
I actually filled the pool in the anti-clockwise direction to be sure that any clockwise motion we see is not due to the way I filled the pool.
So let's let the water settle for a complete day so that we know that it's perfectly still.
And I've left this water sitting here for 24 hours. So it seems like I've damped all of the motions from the filling.
Well, I'm not going to reach in and pull a plug out because that would induce some vorticity. I'm going to use this valve that I have connected to the bottom of the pool.
I really hope this works. Destin, wish me luck.
Good luck, Derek.
I'm about to pull the plug.
Okay, opening the valve in 3, 2, 1. Water should be flowing.
And the pool is draining. But you can't see any motion of the water just yet.
Okay, water's been flowing for a couple of minutes and I haven't seen anything yet, so we're gonna put some dye in it.
To help us see where the water's flowing, I'm gonna put some food coloring in on the 4 cardinal directions around the pool.
Check it out, it's like a tornado, like right off the bat. We got a counterclockwise rotation. We filled it up clockwise and now it's going counterclockwise.
You can clearly see that the water is flowing clockwise in this direction, and that makes sense because that's how it should flow in the southern hemisphere due to the Earth's rotation.
We have a kiddie pool in my garage and the whole Earth is rotating and the water's going counterclockwise because I'm in the northern hemisphere. It's real. This is real.
But you can see what a tiny little effect it is and what extraordinary lengths I had to go to see this effect. So really, you're not going to see it in a bathtub and you're not going to see it in a sink or in a toilet because there are other sources of angular momentum that totally wash out this effect.
We just proved it because we just eliminated variables. The Coriolis effect is real.
There you have it. It works. To understand how it works, imagine a pool with one edge touching the South Pole.
Think about a pool near the North Pole.
The pool is stationary relative to Earth, but every day it's actually completing one full revolution.
The Earth is spinning on its axis, so the pool spins around the pole once a day.
Now you can see the side of the pool furthest from the pole travels much farther every day than the side right next to the pole.
The whole pool is moving, but the part that's closest to the equator has more momentum, and the part that's closest to the pole has less.
So the outer side of the pool is moving fastest towards the east, and as you get closer to the pole, the velocity decreases down to 0.
Think about these velocities relative to the drain in the middle.
Now imagine we drain the pool.
When we pull the plug, all the water starts moving towards the middle.
Water from the far side is moving too fast relative to the drain, and so it gets out ahead, whereas water from near the pole is going too slow, and so it lags behind.
The side nearest the equator is going faster, so that water outruns the drain. But the water nearest the pole is going slower, so it falls behind. So when the water approaches the drain, it swirls counterclockwise. This is the reason hurricanes swirl counterclockwise in the northern hemisphere.
And this is the reason cyclones swirl clockwise in the southern hemisphere.
The center of the hurricane has lower pressure, just like a drain, so the hurricane swirls just like our pool.
The higher pressure air rushes into the eye of the storm, and just like in our pool, swirls in the direction dictated by the hemisphere.
And that's the truth about toilet swirl.
Now, pretty cool video, right? I mean, it's pretty awesome stuff that they did to put those two videos and link them together so well. I want to talk a little bit about this picture right here. This map of the world shows you the direction of the winds going across the surface of the Earth. Now, this is a really cool colored version of it, and we're going to be talking about a lot more of this stuff when we get to some meteorology stuff in a couple weeks. But I want to show you guys your reference table, because this same picture is in your reference table on page 14. So if you can get your reference table out and go to page 14, that's right here, and you'll see this planetary wind and moisture belts in the troposphere, so the lowest layer of the atmosphere. And you'll see this picture of the Earth right here in the direction of the winds. And I have that same picture right here. I'm going to edit it right here. So if you take a look, let's draw a line down the middle here. That's the equator. So everything up here is the northern hemisphere. I'm going to move my picture out of the way. Actually, you know what? I'll just get rid of myself. All right, so let's use orange for the northern hemisphere. Okay, so here are the southwest winds, and here are the northeast winds. This is the northern hemisphere. I'm going to write NH up here in orange. Okay, so if I were to say, okay, let's deal with the southwest winds. Pretty easy. It starts right here. If it were to go straight, and if you remember that first video, if it were to go straight, it would go straight up like that, from the south to the north. However, as you can see by the arrow, it's actually getting deflected or curving to the right. Same is true with this arrow, right? If it were to go straight, it would go like that, but it gets deflected to the right. Now take a look down in the southern hemisphere. Let's use a different color. Let's use blue down here. If I were to draw a straight line from where it begins and go straight up like that, that's not very straight. Oh well. It gets deflected to the left. Okay, and same is true with this one. Okay, there's my fairly straight line. It gets deflected to the left. So in the northern hemisphere, to the right. in the southern hemisphere to the left. Now you're saying, well, what about these guys down here? They don't look like they're going to the right, and neither do these ones. They don't look like they're going to the left. They look like they're going the opposite. So what you have to do is you have to flip the picture upside down. Okay, so I'm going to do that. I'm going to flip this around like this. Aha, okay. Go back to my brushes. All right, so northern hemisphere is up here, and so I'm going to use orange again. Here's that same picture, right? The same northeast winds, but now it looks like they're upside down. So I'm going to go straight, right? And look, the arrow deflects to the right. Same is true with this one. Again, deflecting to the right. In the southern hemisphere, back to blue, starts here, straight line, it gets deflected to the left. And same as with this one, right? It's deflected to the left. So again, big takeaway is northern hemisphere deflects to the right, southern hemisphere deflects to the left. Now that's going to have a direct influence upon the currents, and this is page 4 of your reference table. So let's deal with a really simple one. Let's start by just drawing the line for the equator, which is right here, 0 degrees. Okay, so my northern hemisphere is up here, and my southern hemisphere is down here. And so up in the northern hemisphere, everything is getting deflected to the right. So let's deal with like the Gulf Stream current. That's a fairly easy one. I'll draw a black line like this. It's starting here, okay, and you would say, okay, it would go straight. It would run into North America, but it would go straight, but it gets deflected to the right, right? And that's all due to the fact that the Gulf Stream current is located at approximately over here, around 30, 40 degrees north, right? So right in this region. So if I look at my other map, I flip this back around again. Should have done that before. Okay, 30 or 40 degrees north is like right in this area. So the southwest winds are curving to the right. Okay, and if you go back to the picture here, that makes the Gulf Stream current curve to the right. Okay, same is true with the Canary current. It actually curves to the right. And it looks like it's not, but if you draw a straight line like this, that's curving to the right of that line. Same is true with the Kuroshio current, right? It would go straight like this, but it curves to the right because of the air curving to the right. Now what about down here, southern hemisphere? Well, if you look at one of them, let's say the Peru current right here, it curves to the left, right? Curving to the left. Same is true with the, what's this one called? The Benguela current, right? Curves to the left. Okay, same is true with the East Australian current. It's actually curving to the left, this way. Okay, so the idea and the big takeaway from this whole thing, guys, Coriolis effect is due to the rotation of the Earth. Okay, back to this. It's due to the rotation or the spin of the Earth every day. And as a result, the air is going to deflect or curve one way or the other, depending upon where you are. And if you're in the northern hemisphere, it curves to the right. If you're in the southern hemisphere, it curves to the left.